and welcome guys. Now in this video what we will be doing is implementing the all three different type of gradient descent that we have discussed in the previous video. So this whole implementation will be done using plain NumPy code, so that we understand this algorithm thoroughly, as well as we will use Scikit-learn to do this as well towards the end of the video. Okay, so let's start with the plain code first. So first we'll import a NumPy. Okay, now we'll create a function to generate a synthetic data. Okay, so def synthetic data. Okay, x equal to p dot random let comma 2, and we'll generate y equal to 1 plus 2 into x all and we'll return the x and y. Then we'll create one more function for calculating error, MSE. Okay, so we have to pass the prediction and the actuals. So MSE equal to, the formula is mean of prediction minus actual whole square. And we'll return it. Now we'll create a three different function, one for batch, another for stochastic, and third for mini batch. Okay, so let's define for batch first. So okay, here we'll take x, y, learning rate, and epochs. Okay, so first of all we need to create MNN, which is x dot shape. Then our theta will be for now np dot zeros of shape n of n size. Okay, so let's calculate the time as well. Start time equal to okay, so let's import time also. So for epochs, in range of epochs, calculate the predictions. Then we'll calculate the gradient. Which is 1 by m into x dot transpose dot product of errors. We'll update the theta, which will be minus equal to learning rate to gradient, and time so the training time will be end time minus start time. Okay, and we will return theta as well as train time. Now what this code is doing basically, so basically it takes x and y, which is a matrix representing the input feature, where each row represent data point and each column represent a feature. Y is a vector representing target value labels. Okay, learning rate is a hyperparameter controlling the step size of each update in the gradient descent process. Epochs is the number of iteration passed through the entire data set, so the gradient descent algorithm should perform. M comma n equal to x dot shape basically is doing the line extracting the number of data point m and the number of feature n for the from the shape of input feature matrix x. Now we are defining theta. So initializing the parameter vector theta as a NumPy array with zeros. Theta contains the coefficient of each feature and is the parameter that algorithm tries to improve. Okay, now we are storing some start time. Now we are running a loop with iterating the specific number of epochs. Now we are calculating the prediction by performing a matrix multiplication of feature matrix x and the parameter vector theta. sorry. So this computes the predicted value for all the data points. Now we are calculating errors. So basically we are subtracting prediction minus actual target. Okay, so this error represents the difference between the predicted and actual value for each data point. Now calculating the gradient, so which represents the direction and magnitude of the parameter which updates needed to minimize the mean squared error. So the formula used here involves transposing the feature matrix X and performing the matrix multiplication with the error. So the 1 by m factor is used to scale the gradient by the number of data point to obtain the average gradient. Lastly, we are updating the parameter vector theta by subtracting the product of the learning rate and gradient. So this step is where the actual optimization of the model parameter take place. Lastly, we are storing end time and calculating the training time and returning it. Hope this is clear. Now let's write the code for stochastic gradient descent, okay, as well as mini batch. Okay, first few lines should be same. Okay, so just copy from here to here. Now what we'll do, we'll just rename it. Stochastic gradient descent. Then input parameter will also be same, m and n. We are storing m and m, then theta start time, and we are running as per whatever the number of epochs we have. Then we will calculate the predictions. Okay, so the predictions will be x of comma all and their dot product theta. Error will be prediction minus y of I. Then we have gradient, which will be 1 by m into x of I dot t dot product of error. And then we'll have theta, which is minus equal to learning rate into our gradient. Again we'll calculate the end time and training time. So this will help us which algorithm is taking long time, which algorithm is not taking long time. So like we have discussed during the advantages and disadvantages discussion. Okay, and here we'll see does it actually saying correct or not. Okay, now the next last one is mini batch gradient descent. Again, let me explain you what happening here is. Get some space. So again same thing, I mean x is like a matrix representing input features, y is the vector representing target, learning rate is hyperparameter controlling the step size, epoch is the number of iterations, and m comma n is like a number of features and number of rows data points in the feature matrix X. Now let's again we are doing the same thing. We are initializing the parameter vector theta, which is zeros containing the coefficient of each feature and its parameter that we will be optimizing. Okay, then we're storing the start time and running a loop. So first what we are doing is we are calculating the prediction by performing matrix multiplication of feature matrix X and the parameter vector theta. This computes the predicted value of all data points. Then we are computing the error by subtracting the actual target value y from the predicted value. This error represents the difference between the predicted and actual value for each data point. Then again we are calculating the gradient, which represents the direction and magnitude of the parameter updates needed to be minimize the mean squared error. So the formula used here involves transposing the feature matrix X and performing the matrix multiplication with the error. So the 1 by m factor is again used to scale the gradient by the number of data point to obtain the average gradient. Then we are updating the theta by subtracting the product of learning rate and the gradient, and then calculating the training time. Okay, so let's create the last one, that is mini batch gradient descent. Again some of the thing will be same, so just copy the whole thing. Okay, so just remove this part. Okay, now here we'll again create a one more loop. So for I in range of 0 comma m comma batch size, because here we are including batch size also. Okay, so let's rename it mini batch. Okay, so now batch of x equal to x batch size comma all. Same way for y. Because it's a 1D array. Now we'll calculate the predictions equal to batch of x dot of theta. Okay, then errors and then gradients. Predictions minus batch y. Now theta, no, sorry, gradient first. Gradient equal to 1 by batch size into batch of x transpose dot error. Okay, now what we'll do, we'll update the theta parameter, which is minus equal to learning rate into gradient. So it's done again. Let's rerun it. Now let's create a main function where we'll call all of this. Okay, so def main x comma y. So let's first generate synthetic data. Okay, and then we'll train the linear regression model using batch gradient descent. Okay, so theta batch equal to, okay, it should be inside. Okay, we will have one more parameter coming, that is training time for batch gradient descent. Okay, batch gradient descent will we have to pass x and y as well as learning rate, which is 0.01, and then number of epochs. Okay, so let it be 1000 for now, and then we'll create the mean square error of batch. Okay, so calculate MC, and we'll pass x dot theta batch comma y. Okay, which is actual. Now let's copy this code 2 times. So this will be renamed as theta stochastic. Okay, now this will be a stochastic gradient descent function. X and y learning rate and epoch should be same. Okay, now here we will pass theta stochastic and training time stock. Same thing here also, theta mini batch now here we will call mini batch gradient descent, and here we also have to pass one more parameter, that is batch size. Okay, let's give it 16. Okay, you can give anything multiple of 16, like 32, like 64, like that. Okay, so this is also done. So time mini batch. Now what needs to be done is formatting. Okay, so print gradient descent method. Okay, then we'll tell MSE, that is mean square error, then training time in second. Okay, yeah, so let's print all of them. Print first is batch gradient descent. Okay, so we'll use print format to format all this out. Then training time dot format. So first is MSC batch, then training time batch. Now just copy this code 2 more time. Second will be stochastic, then will be mini batch, okay, okay, now let's run it and we'll see the outputs, how they're performing. Okay, hopefully there shouldn't be any error. Okay, let's call the main function now. Okay, if name equal to main function. Okay, so it is saying stochastic gradient descent is not defined. Okay, let's run all of them. Now it is saying I is not defined. Okay, predictions stochastic gradient descent. Okay, here also there will be one more loop for I in range of m. Okay, now let's rerun it, restart the kernel. Okay, now we have mini batch got unspected batch size. Okay, we haven't defined batch size here. Now another error, that is too many indices for array. Okay, batch x. Okay, so let's see. Okay, we have a comma here extra. Let's remove that. Okay, let's run it. Okay, none type has format. Okay, we are getting some empty value, I guess. Let me check why. Okay, I guess the error is in format. Oh yeah, so the close shouldn't be here, so it should be outside. Okay, so we hopefully, I don't think we have any error right now. Let's run it again. Okay, yeah, you can see that we have the result for all of them, and almost we can see that the difference is slightly less. I mean, they are reaching a certain mean squared error, which is very less, and you can see that the least amount took by method, that is batch gradient descent, which has took 0.0 very slight, not even a millisecond, 7 millisecond. Okay, so this one took around round up 1 second stochastic gradient descent. Then we have mini batch gradient descent, which took around 0.04 second. Okay, so now we got right which perform best, because batch gradient descent perform best in terms of number of you know uh, second which it took. It was very faster than other two gradient descent. Now let's implement the scikit-learn version and then see what is the different. I mean, obviously different will be won't be much, only the coding part. You can see that these three part won't be there. Okay, since we wanted to understand thoroughly, that's why I explained this way first. Now let's implement the easiest way by using scikit-learn library. So now we will have clear understanding why we are getting such a output, and I mean how it is different from NumPy implementation. Okay, so let's do that. Okay, and guys, remember I will be adding all this notebook inside GitHub repository. You will find the link in every video in the description box. Okay, so let's first implement all the import all the libraries, that is import NumPy as np. Next is from scikit-learn datasets, import make regression, which will be used for creating the dataset. Now let's import linear model, regressor, stochastic gradient descent regressor. So we will be making all three regression implementation using SGD regressor only. So we'll do batch, then stochastic, and then mini batch. So see how I do it. Okay, so first of all, let's create the dataset, synthetic dataset. Okay, so x comma y equal to make regression. We have to pass number of samples, let's say 1000. Okay, now we have to give features also. Let's give 5. Okay, and we have to add noise equal to 0.2, let's say, and random state equal to 2. Okay, so we have created our data set. Now we have to reshape our target. So let's do it. Y dot reshape -1. So this is required for scikit-learn method. Okay, now let's do the coding for batch gradient descent. Okay, batch gd. equal to SGD regressor. Here we'll pass learning rate equal to constant, so it will automatically constantly it will change. Then our then we have to give ETA 0 equal to 0.01. okay, max iteration equal to 100, and let's not give any penalty, equal to none. Okay, now let's fit the model. Okay, batch GD dot fit xy batch GD coefficient equal to batch GD dot coef. Okay, now if you want to see intercept also, that is also possible. So batch gradient descent intercept equal to batch gradient descent dot intercept underscore. Okay, so basically what here learning rate constant as well as ETA 0 means is, so learning rate obviously it is a hyperparameter that control the step size when updating the model parameter, that is weight or coefficient during the each iteration of the gradient descent algorithm. So it is take a different value, such as when we are taking constant, or you can also select optimal or inverse scaling. So these are specific floating point value. Each value correspond to different learning rate strategy, and the constant that we have selected is this strategy use a fixed learning rate that is specified by the ETA 0 parameter, that the learning rate remains constant throughout the optimization process. So ETA 0 is the initial learning rate when using a fixed constant learning strategy. So it serves the starting point for the learning rate. In some cases you want to set an initial learning rate that is relatively large and then adjust it based on the optimization progress. Okay, so the value of ETA 0 depend on your specific problem and the data. So the common practice is to start with a small value, that is 0.01, and then experiment with different value to find that the result is effective convergence or not. Okay, and that is the reason of giving this way. Now let's code for remaining. So next is our stochastic gradient descent. So here again the learning rate will be constant, ETA will be 0, max iter will be 100, and penalty will be none. By only making one change, shuffle equal to true, it becomes stochastic gradient descent. Okay, now you understand, right, what is the difference between above and the batch gradient descent and stochastic. It's just a simple thing. Okay, now let's code for the third one also, that is mini batch. Okay, so let's change the variable names. SGD okay, so we have coded for that as well. Now what we will do here, also we have to make our shuffle equal to true, as well as there is also one more parameter, that is average equal to true. Okay, so this is what make it it has a mini batch gradient descent. Now let's run this, run all these codes. Okay, shuffle spelling is wrong, I guess. Okay, so we have trained all our different gradient descents. Now let's print out the results. So print batch gradient descent. Okay, now print the coefficient. Okay, so we have stored it already. Same thing. Now intercept. Okay, same for remaining two. Stochastic and mini batch. So just change the names. Okay, so let's run it. Okay, now we have the value for all of them. So basically, so these all three type of gradient descent. The coefficient attribute represents the estimated coefficient, that is slope, for the linear regression model. So the intercept attribute represents the estimated intercept, that is bias, for the linear regression model. Okay, now obviously the goal is to estimate the coefficient that minimizes the mean squared error, or you can use another loss function also depending upon the chosen gradient descent algorithm. Now the question is how to interpret these values. So high positive coefficient indicates that the predictor value has a strong positive impact on target variable. For each unit increase in the predictor, the target is expected to increase by an amount proportional to the coefficient. So the high negative coefficient indicates that the predictor variable has a strong negative impact on the target variable. So for each unit increase in the predictor, the target is expected to decrease by an amount proportional to absolute value of the coefficient. So the coefficient value value close to 0 suggests that the predictor has a weak influence on the target variable. And the intercept value, the expected value of target variable when all the predictor variable are 0, it is a point where the regression line intersect the y-axis. So high positive intercept means that the expected target value is higher when all the predictors are 0. A high negative intercept means that expected value is lower when all the predictors are 0. So you can see that more and over all of them are performing almost same. There is very slight difference in between the second coefficients. So yeah, this is what how we implement sklearn using sklearn, and hope you learned how to implement using NumPy and sklearn. And now it must be there must be some question. If you have some question, please write down on description. I'll must reply on those whenever I get some time. Okay, so thanks for joining this class. I think you guys have learned so much thing until now, and now we will be moving towards another algorithm, that is logistic regression. And moving forward we will be learning very complex algorithms also. So linear regression was very simplest one. Obviously there were multiple methods which will take some time to digest all of this thing. But just remember one thing, all of this thing that you are seeing here is a very huge number of methods and things. Just remember guys, this won't be you won't be doing these many things in the actual data set. When you will be on actual data set, you will be you will have predefined number of things that you have to do. First of all, obviously understanding the business, it will take 10% of time. Then we have our data set, preparing it, pre-processing it, feature engineering, doing normalizing. All this thing will take almost 70% of your time. So modeling just take 10 or 15% of time, and then after that documentation and productionizing. So these whole the data preparation time is the most crucial time, where most of the time goes. Okay, this modeling won't take any time, because it's just a 2 line of code that you will be writing and implementing the whole algorithm just by these 2-3 lines of code. Okay, the whole time, your whole time throughout the project will go for preparing the data that you will be feeding to the model. So that is what important part is. That is what where you will prepare how that model should be learning, what model should be learning, and what will be the most important feature that you want to teach your model to be to basically understand the target variable. So this is what I wanted to give a note. So see you in the next tutorial. Thank you for watching. Bye bye.